So this is a short section on what are called tunnel junctions. And this is a special case of a p-n junction which gives two important effects. It gives a large current in reverse bias, and it also gives a funny phenomenon of negative differential resistance. So first, let's look at where you might use a tunnel junction these days. So the example I always point to is in what's called a multi-junction solar cell. So you can construct a multi-junction solar cell by having two cells stacked on top of each other, with the top one here having a larger band gap, and then the bottom one here being made of a smaller band gap material. So when the sunlight shines on this solar cell, this junction goes into forward bias, but this junction is actually transparent for photons below its band gap, and so those photons make it down here. So for example, this one might catch the blue and the green, and this one only catches the red photons. So the problem is that if we just sandwich these things together, we would end up with a p-n junction of the opposite polarity between these two parts. So what we need to do is have a way to connect these two solar cells electrically so that a current can flow through the whole stack of them, but it should have very low resistance at whatever voltage we put it into, and this should occur under reverse bias. So the solution here is that you actually insert a very, very heavily doped p-type layer there, and a very, very heavily doped n-type layer there, and then sandwich them together. And let's talk about why that works. So this, this double subscript here, I'm taking to mean that we've actually doped the n-type side so high that the Fermi level is actually above the conduction band. And similarly, on the p-type side, we've doped it so high that the Fermi level is below the valence band. So whenever we put two dissimilar pieces of material together, they're going to form a built-in voltage, which is given by the difference in the Fermi levels. So in our case here, the built-in voltage is actually going to be larger than the band gap. So when we actually bring these into contact, the band diagram is going to look sort of like our old band diagrams for normal p-n junctions, except the built-in voltage is very large, so that it sort of mimics, in a sense, the effect of a reverse bias in our previous case. So here's our Fermi level, and as you see on this n side, we have a whole bunch of electrons here, and on the p side here, we're full of electrons below here. So now if we add even a tiny infinitesimal voltage, forward bias voltage here, we can actually get tunneling to occur between these electrons here and these hole states here. Now, why tunneling is significant is, remember that the densities here, the doping densities, so Na has to be greater than our effective density of states. So we're talking numbers, doping numbers in the 10 to the 19 or higher range for silicon, and similarly on the n-type side. So we have incredibly high doping on both sides, which actually means that our depletion width is incredibly narrow. And we're talking nanometers here, not microns. Now, if we look at the actual band diagram and we think about how an electron would get from this side to this side, well, we can kind of see that it faces a tunnel barrier given by this shape, and we could actually approximate that sort of like a triangle, with the triangle's height being the band gap approximately, and the triangle's width being given by the depletion width, controlled by the same equations we've already derived. So in forward bias, remember the depletion width is even getting smaller, and so our tunneling probability is going up exponentially with the applied voltage. So what does this look like on the IV curve? Well, this is a different kind of current than the normal forward bias diffusion current we've been talking about. So here's our normal forward bias JV curve for a plain old PN junction. But because of this overlap, this band overlap here between the conduction band and valence band, which is induced by the degenerate doping on both sides, we actually induce this extra tunnel current, which happens up to a point here. Now, if we look carefully and think about this, if we go into high enough forward bias, our electrons here are actually going to only be above this conduction band. And if we add enough voltage that we bring the conduction band higher than the valence band here, we can no longer tunnel into these states. So we know that this current has to turn around and come back down here in forward bias. And it's this weird behavior here which gives you a region of negative differential resistance. So again, if we take the slope at any point, the slope is 1 over r. Here the slope is negative. So effectively this is a region where the diode could be adding gain or actually adding power instead of dissipating power to a signal. These currents and voltages are rather small though, so it's not an effective amplifier. So the total current eventually, as you add more and more forward bias, eventually you pick up again with your diffusion current and you join that curve. So the total current in forward bias has to look like this, a little hump given by, and then the regular exponential increase. Now in reverse bias, if we keep reverse biasing this, well, the overlap between these bands just keeps getting bigger and bigger. So instead of saturating the voltage here, which we do in the reverse bias case for a normal PN junction, we actually keep on increasing in reverse bias, still through the tunneling mechanism. Eventually it will start to get a little bit smaller because the depletion width will be expanding too, although that's a small effect because of the high dopings again. So back to our solar cell example over here, what does this do for us? Well, if we have, and we're going to jump ahead in the book just slightly here, if we have the illuminated JV curves for these two solar cells, and now I'm going to use red for this bottom one and green for this upper one. So the illuminated JV curve might look something like this for the green one, and something like this for the red one. And if we have a nice tunnel junction between them, what it means is that we can add the voltages. So we take the red voltage here and we add it on, and our overall series connected tandem solar cell should have an IV curve that looks like this, the blue one, the total current and voltage going through the device. So if our resistance is very small in the tunnel junction, we get the addition of these voltages effectively. And lo and behold, if we look here in the reverse bias part of this tunnel junction. We take R1 over R, and this is steep. The slope is very steep or large. That means the resistance is very low. So we've satisfied our need for a low resistance connection between these two solar cells. The last thing to mention about a tunnel junction is that it, just like a PN junction, serves also sort of as a transformer of carrier type. So if we look here, our current is carried out of this solar cell by holes which are going into this direction into the p-type material to recombine with the minority electrons. And on this side, our current is being carried by electrons. And so the tunnel junction actually serves to convert an electron current into a hole current. And another way of thinking about a tunnel junction is that it's a very efficient device for causing recombination in a very small area. Okay, so that's what we need to think about for tunnel junctions. They're a special case of PN junctions with very high doping on both sides. And most of their behavior can be understood in a similar fashion to the considerations we made for the Zener breakdown mechanism on a normal PN junction, except that we also have some phenomena happening in forward bias because of the induced band overlap by the degenerate doping on both sides.